Okay, so far we've been talking about electric potential. Now we're going to talk about how electric potential is related to Gibbs free energy or spontaneity. So we learned previously that if our E cell is positive, the reaction is spontaneous. So when we talk about spontaneity, we're talking about delta G. Well, there are two equations that we need to be concerned with for Gibbs free energy and electrochem. So the first one is a new equation, and that's that delta G delta G is equal to negative N times F times E. Well, E is just going to be our E cell. N is going to be our number of moles of electrons transferred. And you can simply look at the half reactions to see how many electrons have been transferred. So if I have this particular reaction right here, I know that 5 moles of electrons have been transferred here. So I'm just simply looking at the coefficients in one of the half reactions. We can't really look at the full balanced reaction because remember, we're taking the electrons out when we write the net ionic balanced reaction of a redox reaction. So N can just simply be retrieved by looking at one of the half reactions. Now F is Faraday's constant, and that is equal to 96,485 joules per volt per mole. So that tells you how many joules of energy is released per volt and per mole of electrons. So we can get delta G, so we can determine if a reaction is spontaneous or not by multiplying the number of moles by Faraday's constant by the E cell. And remember, if delta G is negative, then the reaction is spontaneous. Well, this equation we learned previously, and that is that delta G is equal to the gas constant times the temperature in Kelvin multiplied by the natural log of the equilibrium constant. So sometimes this becomes important in electrochem as well. So all of these three things are related. K, delta G, and E are all related. So if we are looking to see if a reaction is spontaneous or not, we don't actually have to do a calculation. Sometimes we can just simply look at what we're given to determine that. So right here, well, I know that if E cell is positive, then delta G should be negative. And if you look at the equation right here, we have negative 1 times N. Now, N will never be negative because it's the number of moles of electrons. You can't have a negative mole. Faraday's constant will always be positive as well, but E, if that is positive as well, then you're multiplying 3 positive numbers by negative 1, so you're going to get a negative number. So if E is positive, then the reaction is going to be spontaneous because delta G is negative. Now, in cases where E is positive, you'll find that K is greater than 1. So if we have a reaction that is spontaneous, usually we'll see that K is greater than 1. Okay, so now if we get to a situation where E is actually equal to 0 and K is equal to 1, then we'll see that delta G will also be at 0 as well. And really what that means is that we're at equilibrium. So if these two components, if E and G are equal to 0, then that means we're going to be at equilibrium. And if you look at the equation right here, well, if E is 0, we should get 0 for our delta G as well. So in that situation, we're going to be at equilibrium. Now, when we have E cell and it's negative, we'll end up with a positive number. And if we have a positive delta G, that means we're not spontaneous. But the reaction would be spontaneous if it was going in the reverse direction. So if we have a reaction that's maybe reduction and we're looking at it and we have a positive delta G in the opposite direction, it's going to be spontaneous. And then in these situations too, K should be less than 1. Okay, so let's look at an example of something you might see. So for this particular reaction, what is N and what is delta G? Okay, so first thing, let's figure out what N is. And if I look at this reaction right here, this is the full redox reaction, which means we're not looking at the electrons because they were canceled out. So what we can do, since it's already balanced, we can just look at one of the half reactions. So let's look at the iron. Iron goes from a positive 2 to a positive 3. So right here we have the oxidation reaction. So let's look at that. So I have 5 iron ions, and they're being oxidized. Okay, so now what I need to do is I need to figure out how many electrons I would need to balance this reaction out. So I'm going from a 5 times 2, so a positive 10 here, and a 5 times 3, so positive 15 here. So I'm going to add electrons to the more positive side. I'm doing this because I'm trying to figure out how many electrons were transferred in this particular reaction. Well, if I'm going to balance, I need to bring it down to 10, so I'm going to add 5 electrons here. So my number of moles of electrons will be 5. So N is going to be equal to 5 here. All right, so now it's asking for delta G. And by the way, if you'd picked the other half reaction here, it would be the same thing. You would still see that it's going to end up being 5 electrons here. Because we have a positive 2 on this side, we have a positive 7 here. We would need to give it 5 electrons to make it come down to positive 2. So this is the other half reaction here, and N is still going to be equal to 5. So it's asking for delta G now. Well, delta G is equal to negative N times F times E. Well, we have N now. We have F is a constant, so we just need to get the E cell. So when I look at these two reactions right here, this is the oxidation reaction, and I go from a plus 7 to a plus 2 here. This is being reduced, so that's my reduction reaction. And there is a piece of information that is missing here, because if you go and you look up the E values, you'll find the iron, but you won't find the permanganate here. So I'm going to give you that number. So for this particular reaction, the E is equal to 1.51. All right, so now if I look up this value was found on the table. E, it was equal to 0.77. So we need to take the difference to figure out what the E cell is of the entire reaction. Well, remember, you can plug it into the equation if you can remember which one is being subtracted from what, or you can just simply remember that if it's being reduced, then this value can just be left as is. If it's being oxidized, it's going to be the opposite. So you will take the sum after you figure that out. So if I'm looking for E cell, if I remember, it will be the E reduced minus the E oxidized. If you remember that, great. If you don't, remember that anything that's being oxidized will have the reverse number here. So this would actually, since it's being oxidized, it will be negative 0.77. And then just take the sum. All right, so this is being reduced, so I don't touch 1.51. And then this is being oxidized, so it becomes negative. And I put those two numbers together, and I'm going to get 0.74 volts. So the E cell should be 0.74. Oops. All right, so at this point we have our N, we have our E cell. Now we're going to plug everything into the equation. We have N, we have E, we also have F. F is a constant, which is 96,485. That's going to be joules per mole per volt. Okay, so we have N. We can just simply plug it into the equation to get delta G. N is 5. F is going to be this. And then at the end, we have our voltage, which is 0.74. All right, so now when we solve for delta G, we're going to get negative 357,000 joules. Or you can even just say it's kilojoules. It depends on what the problem is asking for. But usually it's going to be kilojoules because joules are pretty small. So at the end, we'll get a negative delta G, which means the reaction is spontaneous, which should happen because our E cell is positive here. All right, so at this point, we're going to discuss electrolysis. Electrolysis is basically the opposite of a battery. So whenever we set up a galvanic or voltaic cell or an electrochemical cell, we're creating electric energy because it's a spontaneous reaction, so the electrons just flow from one anode or from one electrode to the other electrode. Now, in electrolysis, it's the exact opposite. Instead of generating electric energy, we're going to put in electric energy and force a non-spontaneous reaction to happen. So we're going to take two electrodes that will not have a spontaneous reaction, and we're going to force that reaction to happen by applying energy or electric energy. So basically, we are going to add the power of a battery to make this reaction happen. One of the other differences between electrolysis and electrochemical cells is that there's only one cell. In electrochemical cells, you set up two half cells, but in electrolysis, you're just going to put everything into one cell. Okay, so this is what an electrolytic cell would look like. It's one cell. And basically, you're going to have a solution with cations and anions, so there's no need for salt bridge here. You're going to have your anode and your cathode, and it's going to be attached to a battery. So what will end up happening here is that anions in this solution will be attracted to the anode. So remember, anions are negatively charged, and what will happen is that those anions will lose their electrons, and then will go into the anode and then travel through the anode and then go to the cathode. Well, now that we've got electrons here, the cations in the solution, so the positive ions, will be attracted to those electrons, will come over to the cathode, and then they will be reduced. So they'll gain the electrons on this side and lose them on the anode. And that's still the same in an electrochemical cell. So here at the anode, we're going to have oxidation happen. So the anions will lose the electrons. The electrons will flow through the wire and then go to the cathode. And then the cations in the solution will be attracted and then gain those electrons. Okay, so if I look at this particular reaction right here, well, I have chlorine becoming chlorine gas and then potassium becoming potassium as a solid. Well, this is definitely a non-spontaneous reaction because potassium is one of the very reactive metals. It's in group 1. So remember, if I put that into water, it's very, very reactive. It likes to become the cation. It likes to lose electrons. So if we're trying to make it gain those electrons, that's going to be a non-spontaneous reaction. The only way that you can do that, this particular reaction, is by adding electric energy. Well, it's the same thing for water. I can split water into hydrogen gas and oxygen gas. I can do that if I apply electric energy. So if you have an electrolytic cell and you place it into water, it becomes a little bit more complicated because this is one of the reactions that can happen, or you can have a reaction like below, right here. The arrows got misplaced here. But anyway, if you have a solution and you place it into water to do this electrolytic cell situation, sometimes you have to consider what the E values of these two reactions might be. Okay, so whenever we're looking at these cells, sorry. Of course. Okay, so there are various questions that they could ask you about electrolytic cells. One of them could be in regards to this particular equation. So anytime that we have a problem in which we will have to determine an amount, this will probably be what you're going to be looking at. So you're going to be looking at this particular reaction and also stoichiometry. So the amount of a substance can be produced, the amount of the substance produced in electrolytic cells can be calculated with this equation right here. So it depends on how much current is running in the reaction and how long you let it run. So Q is the charge measured in coulombs, I is going to be the current measured in amps, and then T is going to be the time measured in seconds. And what we do is we can calculate the charge in coulombs if we know the current and we know how long it's been running. And really the charge is measured in coulombs. We can convert the coulombs into Faradays. And remember, a Faraday is equal to 1 mole of electrons. So if I know how many moles of electrons have been transferred, I know how many grams of a substance can be deposited on an electrode or vice versa. So we're going to be looking at this reaction right here, and then the rest of it will be doing conversions between Faradays, moles of electrons, and any other substance that might be present in the reaction. So anytime that we're looking at these problems, we're probably going to be looking at that equation. Coulomb, or charge, is equal to current times time. And then after that, you will be doing conversions. So the number of coulombs can be converted into Faradays because 1 Faraday is equal to this many coulombs. This is also equivalent to 1 mole of electrons. So if I know how many Faradays I have, I know how many moles of electrons, and then I can go to anything in the reaction. Because remember, if I have a half reaction written like this, if I can figure out how many moles of electrons have been transferred, I can figure out how many moles of Fe plus 2 I started with, or I'm going to end up with plus 3. I can figure out anything in that reaction if I know how many moles of electrons have been transferred. All right, so let's look at an example of what you might see. Okay, so the electrolysis of dissolved chloride samples can be used to determine the amount of chloride content in a sample. So at the cathode, the reduction half reaction is this. What mass of chloride could be deposited in 6.25 hours by a current of 1.11? Okay, so let's pull out the information that was given to me first. It does give me the reaction here, and also tells me that my time that has passed is 6.25 hours. It also tells me my current, so current is I, 1.1 amps, and it's asking for the mass of chlorine, so the mass of chloride. Chloride, or Cl minus. Okay. Well, it gives me a reaction, so if I'm looking for the mass of chloride, if I know how many electrons have been transferred, I can figure out the mass of chloride. So this is ultimately what I want if I'm looking at this reaction, I can get my moles of electrons and then figure out what that is. So I know that charge is equal to current multiplied by the time. And if I can get Q, so I don't know what Q is either. I have the current, I have the time, but if I know what Q is, I know how many coulombs I have. And if I have the coulombs, I can calculate how many Faradays I have. And then with Faradays, I can calculate how many moles of electrons I have, and with that, I can get what I ultimately want. So I need to figure out Q before I can do anything else. So I'm going to use this equation. I have I have T. I can figure out what Q is. The only problem is T is in hours, so I've got to convert that first to seconds. So hours needs to be converted to seconds. 1 hour is equal to 60 minutes, and 1 minute is equal to 60 seconds. All right, so when I figure out that, I get 2 to 500. All right, so now I've got my seconds, I've got my current, so I can figure out what Q is. So Q is equal to I times T, which is 1.1. That's my number of amps, and then multiplied by my time that has passed. So Q is equal to this. So the reason I'm looking at that is because that tells me how many coulombs I have. And remember, if I know how many coulombs I have, I know how many Faradays I have, and 1 Faraday is equal to the moles of electron, or 1 mole of electrons. So I can figure out how many moles of electrons have been transferred that way. So let's do that. Let's convert this into Faradays, and then I can convert that to moles of electrons, and then from there I can go to chloride. So I'm going to start with coulombs. That's what I have. Then I'm going to go to Faradays, because I do have a conversion factor. I know that one Faraday is equal to 96,485 coulombs. Then I can go to moles of electrons. Once I'm in moles of electrons, I can go to moles of chloride. Then I can go to grams of chloride. So basically, it's this one equation and then lots of conversions. So we're going to start off with our number of coulombs. All right, so I'm going to go to Faradays first. And put Q as short for coulombs. All right, so 1 Faraday is equal to 96,485. And this number is written on your reference sheet, and I believe they even give you the conversion factor, I think. So 1 Faraday is equal to this many coulombs. All right, so now I know that if I have a Faraday, 1 Faraday is equal to 1 mole of electrons. All right, so now moles of electrons will be on the bottom, moles of chloride at the top. This is moles on top of moles. I'm looking at the equation at that point. So for every 2 moles of electrons I have, I'm going to produce 2 moles of chloride. All right, now we'll just go to grams. So 1 mole is equal to, I believe, 35 grams. I think it's a little bit more, but for the sake of what we're doing right now, I'm just going to simplify it. All right, so then after I go through everything, I should get 9.06 grams of chloride. Okay, so anytime that you have a question regarding electrochem and it's a math question, you're probably going to be using this equation and then doing lots of conversions. Okay, so charge is measured in coulombs, and if I have the coulombs, I can figure out the Faradays, I can figure out the moles of electrons from that, and then go to any substance because electrons can be included in these half reactions. All right, let's look at another example. Okay, so how many Faradays are required to reduce 1 gram of aluminum-3 to aluminum metal? Okay, so it gives me the mass of aluminum. Okay, first of all, let's go ahead and write the equation out. So we're reducing aluminum with a positive 3 charge. So if we're reducing, we're adding electrons. If I want to reduce this down to just the metal, I need 3 electrons to get aluminum as a solid. So this is our reaction right here. And it's asking for Faradays. So I want how many Faradays. All right, and it gives me the mass of 1 gram of aluminum with a positive 3 charge. So this is my starting point. I know that I have 1 gram. And Faraday, remember, is equivalent to 1 mole of electrons. So if I have 1 gram of aluminum, I can go to my moles of electrons, and then that'll tell me how many Faradays I have. So it's just a simple conversion problem here. All right, so we're going to start off with grams of aluminum. Then I can go to moles of aluminum. Then I can go to moles of electrons, because remember, if we're trying to go from one substance to another substance, you have to go through the mole. And then once I know that, I can go to my Faradays, because 1 mole of electrons is equal to 1 Faraday. So I have 1 gram of aluminum. I'm going to go to moles. 1 mole is equal to 27 grams. Go to moles of electrons next. Moles on top of moles, I can look at my coefficients. So for every 1 mole of aluminum, I have 3 moles of electrons being transferred. And for every 1 mole of electrons I have 1 Faraday. All right, so I'm going to go through, do the math, and I'm going to get 0.111 Faradays. So for this particular problem, we didn't even need to worry about the equation of Q is equal to I times T. We didn't have to worry about that this time. So this one was just simply converting between aluminum and then going to moles of electrons, which is the same thing as a Faraday. All right, let's look at another example. Okay, so this one, it says, how long in hours must a current of 5 amps be maintained to electroplate 60 grams of calcium from molten calcium chloride? Okay, so first of all, we're looking for time. It gives me current, so it gives me I, which is 5 amps, just capital A, and then it also tells me that I have 60 grams of calcium. So I have 60 grams of calcium, and it wants to know time. Well, the only thing that I know in electrochem that involves time is that Q is equal to I times T. So I want time. I have current, which is great, but I need Q in order to do this. So I still don't know. I still can't just plug it into this equation because I don't have Q. But remember, Q is measured in coulombs, and we can convert coulombs and Faradays. So if I know how many Faradays I have, I can figure out my coulombs, and my Faraday is equal to 1 mole of electrons. So the first thing I'm going to have to do is I'm going to have to figure out how many moles of electrons were transferred in this reaction. All right, so it's saying that I'm electroplating 60 grams of calcium from molten calcium chloride. So I'm starting with calcium chloride. And remember, this is a redox reaction. Electroplating, electrolysis, anything that's like that, we're going to be looking at the electrons. That's what I'm concerned with. So I have calcium, and I know in this reaction, or in this compound here, it's a positive 2 charge. Well, I want to go from a positive 2 to solid calcium. That's what I want to do. I'm going from this ion to solid calcium. So if I want to do this reaction, I need 2 moles of electrons to do that. So this is a redox reaction. I'm concerned with the calcium in this compound. It goes from the ion to the solid, so that's what my reaction is. All right, so the reason I care about that is because I need to go from my 60 grams of calcium, and I need to figure out how many moles of electrons were transferred with 60 grams of calcium. So I'm going to convert between calcium and moles of electrons, and then that'll give me my Faradays, which at that point I can convert into coulombs, which I need for this equation right here. All right, so I'm going to go from grams of calcium to moles of calcium. And then with that, I can go to moles of electrons. And then that'll tell me how many Faradays I have, which can be converted to coulombs. And once I know my coulombs, I can plug it into this equation right here. So I have 60 grams of calcium. Go to moles of calcium first. I believe it's about 40 grams. Then I can go to moles of electrons. Moles of calcium will be on the bottom. All right, so moles on top of moles. I have 2 moles of electrons for every 1 mole of calcium that I have. Well, I know that if I have 1 mole of electrons, that's equivalent to 1 Faraday. And if I know I have Faradays, if I know how many Faradays I have, I can convert that to coulombs. And that's going to be 96,485. All right, so I'm going to go through, do that, and I'm going to get 289,455 coulombs. So now that I've got my coulombs, I have Q. Okay, so now I have Q, I have I can figure out what T is by using this equation. So now I can just plug it into the equation. I get 289,455 is equal to 5 times T. Divide out the 5. And I get my time in seconds though. So I get 57,891. And then at the end, I need to convert this to hours. So this is seconds. Whenever we plug it into this equation, we're going to get seconds at the end. So now I need to convert this into hours. So convert it to minutes, then convert it to hours. All right, so once I do that, I'm going to get my time of 16.1 hours. Okay, so whenever you have these problems, read to see what information was given to you. If we're dealing with electrochem, you're probably going to be using this equation and then some stoichiometry and conversions. So anytime that you're looking at Q, that is measured in coulombs. Well, coulombs can be converted to Faradays, which is the same thing as a mole of electrons. And using that information, I can go between anything that's in that particular reaction.